So welcome to the second video in our forces topic, and in this video we will look at Newton's first and second laws. So Newton's first law is the law of inertia, and inertia is the resistance of a body to acceleration. So the first law says that objects tend to resist a change in motion. So that is, objects at rest will stay at rest, and objects in motion will tend to keep moving. And this, if you think about it, is completely the opposite of our everyday experience. So we've never seen an object in motion keep moving indefinitely. We always see that an object in motion tends to stop. And so that was the theory for many thousands of years, at the very least from the time of Aristotle in 350 BC, right up until Galileo in 1600s. That was the prevailing theory, that objects tended to stop. And it was actually Galileo who, from his observations of planets and other celestial bodies, he formulated what we know now as Newton's first law. In fact, his formulation was almost exactly the same as we've written it here. So now that we know when we see objects changing their motion, accelerating, we should be looking for the force acting on them. So when we know what to look for, then we can see examples of this law of inertia every day. So, for example, imagine that we have a car with a passenger in the back seat, and the passenger is a stubborn sort of person, and he's refusing to wear a seatbelt. And imagine also that the back seat is lovely, shiny, slippery patent leather, or some such, so there's very little friction between the passenger and the back seat. What happens to the passenger as the car goes around the corner, and why? So I'll give you a minute to pause the video and have a think, and feel free to write your initial explanation in the comment section below. So initially, the car and the passenger are travelling in a straight line at a constant velocity. But when the car turns the corner, his velocity changes, so he's accelerating. And so by this first law, there must be a force acting on the car to cause this change in motion. And indeed there is. So the frictional force between the car tyres and the road is acting to change the car's direction and thus the car's velocity. But what happens to the passenger in this case? So he's not wearing a seatbelt. He's not part of the car. So the force that's acting on the car doesn't act on the passenger. So he keeps his velocity constant, so he keeps going straight ahead. And as the car turns further, he slides along the seat. And eventually he comes to rest, possibly slightly bruised, depending on the driver, but because he hits the car door. So now, once he's hit the car door, he turns with the car, because the car is exerting a force on him. So the car is is changing his velocity. So we've got this one's a very nice demonstration of the first law in action. And Newton's second law now is probably the one that we will be using most often in this topic, although it could be a close call between the second and third laws. And in this law, Newton quantifies the effect of a force on an object. So we can write this law in two different ways, and the first one we'll look at is in terms of acceleration. So we know from experience that the harder we push something, the faster it will go, and that is, so the more force we apply, the larger the acceleration we get. And if we do an experiment and we accurately measure the force produced, the force applied, and the acceleration produced, we get this lovely relationship of Newton's. And that says not only is the acceleration proportional to the force, but it also says that that proportionality constant is the mass of the object. So that is, the mass of an object is defined as the characteristic that relates the applied force to the resultant acceleration. So Newton's second law can also be written in terms of momentum, and indeed that's actually how Newton himself prevented it. So in terms of momentum, so we know that we have F equals ma, and we also know from our previous topic on motion that the acceleration is equal to the rate of change of the velocity. So if we can define ourselves a quantity, the momentum, that's equal to the mass of the object times its velocity, we can see then that the net force applied of an object is equal to the rate of change of the momentum, or that is, the momentum is equal to the force applied to a body multiplied by the time that force is applied for. So the momentum is then a property of a body that determines the length of time required to bring it to rest under the action of a constant force. So in the next video, we have a predict, observe, explain for you. So there's a very nice demonstration of Newton's first and second laws in the tablecloth trick, which will be demonstrated by our lovely Liz.